A real quick video on imaginary numbers. Right? An imaginary number basically solves the dilemma. What happens when, in mathematics, we're required to take the square root of a negative? Right up until probably 9th or 10th grade, your teachers always have probably told you that it's impossible, and it is impossible if you're dealing with numbers in the real set. But in imaginary numbers, right, we say that there is a possibility, that it is possible to do that. And the basic definition of an imaginary number, we'll call it letter I, lowercase I, is that's equal to the square root of -1. All right. If we kind of expand that a bit further, right, and we look at I to the first power and I to the 0 power, right, we can get a nice little list going of values of I, right, and this is important. I'll show you why in a little bit. But we want to think about what anything is to the 0 power. That's just 1. I to the first power, that's I. It also happens to equal the square root of -1 by definition. Now I squared by definition is -1. I mean, think about that, right? I times I is the square root of -1 times the square root of 1, or -1. So it's actually just -1. All right, and that's kind of the weirdest thing, right? If you think about what number can multiply by itself to get a -1, it's impossible, right? It's not -1, it's not +1, it's a fake made-up number, it's imaginary. All right, so I squared by definition is -1, and I think that's like the really key definition to understanding imaginary numbers, that somebody made up a number such that when you square it, it's equal to a negative number. I to the third power, well, that's just I squared times I to the first. So that's equal to -1 times I, or just -I. So I to the third power is -I. Now those are the four basic I to the 0, 1, 2, 3 power, right? The I exponents. And I'm going to put a really nice little green box around those because those are going to be really key to understanding bigger patterns. Right? If you ever come across a problem on a test that asks you what is I to the fourth power, right? What you do is you think about this pattern, because this pattern just keeps repeating over and over and over again infinitely. Well, I to the fourth power is actually, if you want to do it this way, you can go I to the first power times I to the third power. You can do that, right? That's fine, and you'll get something. I'm not really going to do that though. What I want to do instead is come up with some sort of generalization, right? And that generalization basically relies on the fact that we have a repeating pattern of 4 things, right? So if we have a repeating pattern of 4 things, what I want you to do is take that exponent and divide it by 4. And then you get, in this case, a remainder of 0. If you get a remainder of 0, then the answer to your question is the same as I to the 0 power, which is 1. Let's try another one. I to the 10th power. All right, rather than expanding it, I squared, and so on. Right, rather than doing this, which takes a little bit of time, especially if the exponent's really, really big, we want to have a nice pattern, and that pattern again is to take the exponent and divide it by 4. We're always dividing by 4 because there are 4 things here in our pattern. So we get 2, 10 minus 8 is 2, so our remainder is 2. When your remainder is 2, your answer is the same as I to the second power. So this answer is -1. Let's try another one. How about I to the 85th power. Again, 85 divided by 4. That's 2, 8. Bring down the 5, 1, 4. Our remainder here is 1. If your remainder is 1, your answer is the same as I to the first power. So this answer is just I. Okay? And let's do example 4. I to the 43rd power, whatever that is. Let's see. 43 divided by 4, that's 0. That's 3. That's, oh, I see. So there's a remainder of 3. If your remainder is 3, your answer is negative I. Alright, and you can really kind of go crazy with this. Let's in fact do one that's really kind of bizarre. Let's go 2063. If you ever asked for some reason on a test to figure out I to the 2063 power, all you need to do is divide it by 4. And figure out your remainder. In this case, your remainder is 3, so your answer is negative I. So every one of these problems should boil down to one of those 4 possible answers. 1, I, negative 1, or negative I. All right, and this works for more complicated arithmetic. If you had like I to the 52nd plus I to the 302nd. All right, we can do that as well. So you take 52 over 4. Let's see, that's going to be, I think this is going to work out evenly. That's 13 R0. All right, so I to the 52nd power, that's just 1. Plus I to the 302 power, well, let's see, this is 7, 28, 2, 2. So this is R2. R2 is negative 1. So here we have 1 plus negative 1, so that's just 0. And you can come up with all sorts of really, really complicated examples if you wanted to. Maybe I'll give you 1 or 2 more here. Negative 5I to the 35th plus 7I to the 360. Well, first of all, let's figure out what I to the 35th is equal to. This is 8, 32, that's R3. Alright, so R3, if we go back up here, is equal to negative I. Alright, so this is negative 5 times negative I plus 7, and now we want to do the same for this. Right, so we have, let's see, 9 times 4 is 36. So this is R0. That's R0. Alright, that's just 90, remainder of 0. And that, of course, is equal to 1. So this is positive 5I plus 7. We always write the real term first and the imaginary component second. This is called a complex. Called a complex number. One more. Number 8. Alright, 16I to the 10th plus 2I to the 8th minus I to the 90th power. You can pause, try to figure this one out. And I will complete it right here. So we have R2. So if we have R2, that's R to the second, or I to the second power rather, is negative 1. So here we have R0, which is just positive 1. And let's see, 90. That's 2. I'm trying to figure out the remainder. That's 10. 2. That's 8. So that's R2 as well. So it's minus, there's the minus sign. So it's minus, and anything that's I to the second power is a -1. Let's go back up there and check, make sure I didn't make any mistakes. I to the second power is -1. Yeah, that makes sense. Alright, so this is -16 plus 2 plus 1. -16 plus 2, that's actually -14 plus 1, which is -13. So example 8 simplifies all the way down to -13, believe it or not. Alright, so this definitely, we're going to get into a larger discussion on complex numbers soon. And then with complex numbers, we'll do addition, subtraction, multiplication, division, where we talk about conjugates, and we'll have to FOIL, and we'll have to make sure everything's simplified and ready to go. We'll also see how complex numbers graph on a two-dimensional plane, right, and kind of go from there.